Okay, so let's start. Last time we discussed the global structure of Lorentzian spacetime from conformal point of view, and we began discussing the Regge limit. So today we continue with the Regge limit. So just as a reminder, what we mean by Regge limit is this configuration when we have a plane in Minkowski spacetime which contains time and one space coordinate. We have some coordinates x plus and x minus, then light cone coordinates. This plus minus is just x naught plus minus x1. We considered specific configuration where we put operator number 4 at 1 minus 1, operator number 3 at also 1 minus 1, and operator 2 gets boosted in this direction, operator 1 gets boosted in this direction. And we agreed that x, they're all in the same plane, and the coordinates of operator 2 is just minus the coordinates of operator 1. And we also defined, let me just double check so that I don't mess this up. So we defined x2 plus, we called it rho bar, and x2 minus, we called it minus rho. The 4-point function we are looking at is 4-point function of some scalar, just the time-ordered product of phi's at 4 points. So the logic was that if you take this picture and you just boost everything here by half this much in this direction, and everything here in the opposite direction also by half that amount, then you're going to get a configuration. The point 4 gets boosted here, point 1 gets boosted here, point 2 gets boosted here, and point 3 gets boosted here. And in that configuration, the intuition was that points 1 and 3 are creating some initial state, then we have some kind of excitations propagating and being measured by operators 2 and 4. And to get to this configuration, and this particular picture here, which differs by a boost, is just a way of simplifying the kinematics for the actual calculation, just using the boost symmetry. Now, in this picture, we want the operators eventually. If you look, for example, at operator 2, it's going to be an absolute future of operator 3, and space-like from operator 4. Similarly, operator 1 is going to be an absolute past of operator 4, and space-like from operator 3. And this configuration, we can reach it from a configuration where all the points are space-like, so 1 is here and 2 is here, by just crossing this null cone. When 1 is moving here, it crosses the null cone of 4, and 2 moves here, it crosses the null cone of 3. And to figure out what to do with our correlation function, how to analytically continue it into this region, we discussed this epsilon prescriptions, and what we found was that in terms of these guys, we basically need to, when analytically continuing, we need to replace rho by rho bar minus, so we need to replace rho bar by rho bar minus I epsilon, and rho by rho plus I epsilon. So actually replace what we do to rho is not so important because rho will stay smaller than 1. So rho is this distance over here. Well, rho is this coordinate and rho bar is this coordinate. So rho will stay smaller than 1, which is where the problems will begin. But it is the rho bar which kind of forces our operators to cross the cut. And therefore, this is the more important condition to remember. So the goal now is going to be to try to actually compute what happens to this 4-point function in this limit. Before we do that, any questions about the setup? Okay. So to compute this, we're going to try to use the conformal block expansion, or put differently, just the operator product expansion. And if I write out all the operators explicitly, there are a few channels that we can use, a few ways of doing the calculation. So doing operator product is taking, for example, phi at x1 and phi at x2, and replacing their product by schematically by sum of all local operators in theory, with some coefficients in front. So if we do this, then basically this part here turns into one operator, and what remains is the sum over 3-point functions. 3-point functions are fixed by conformal symmetry, so that allows us to compute the 4-point function. Of course, we could also try doing something else, like taking the OP between x3 and x4. Then we replace these guys by O, and again get the sum over 3-point functions. But it turns out that this is equivalent to doing the one between x1 and x2. So if you want to decide which OP you want to take, we decide how to split the 4-point function into pairs, and then we do that OP. So this is one way of doing the OP, but there are, of course, other ways. So instead of pairing 1 with 2 and 3 with 4, we could pair, for example, 1 with 3 and 2 with 4, or you could pair 1 with 4 and 2 with 3. So in general, there are 3 channels there, just determined by what you pair x1 with. If you look at this picture, there is certain kind of appeal to doing x1 with x2, because here, point 1 in this limit becomes almost null separated from point 2, so you might hope that this OP works better than other OPs. And this is half true, half false. So it works better indeed, because this is the way we're going to get the answer eventually. It works worse because this conformal block expansion, as we'll find out, it doesn't converge. So we'll have to do some tricks. Instead of trying to do points 1 and 2, you could try to do, for example, points, let's say, 1 and 4, and 2 and 3. Now, if we do this, this turns out that this converges. This operator product expansion converges. And to see this is fairly simple. Well, this is just a general rule that is true. If you look at this picture, so let me use some different color because it's getting quite dense. So you have operators for here, 1 is here, and 3 is here, 2 is here. So this is a time-ordered correlator. So in this picture, you can imagine that our time runs like this. The constant time slices are like so. So we first encounter 1, then 4, then 3, then 2. And therefore, this time-ordered correlation function becomes so I'll write it phi 1, phi 4, phi 3, phi 2. So I'm just using index instead of writing out the full thing, phi of x1, etc. And what you can see here is that the operators phi 1 and phi 4 act on vacuum state. And when you have a pair of operators acting in the vacuum state, you're guaranteed that the operator product expansion will converge. The reason you're guaranteed this is that in this case, the operator product expansion is nothing other than inserting the complete set of states like in quantum mechanics, in the middle of this vacuum expectation value. So this turns out to be equivalent to operator product expansion in this case. Since this is just an identity in Hilbert space, it just converges on general grounds. Similarly, if you try to take OP between operator 1 and operator 3, you can also make this work because you can imagine that your time now runs in slices like this, so that first you encounter operator 1 and operator 3. Or put differently, you can use the fact that most of these operators are space-like to rearrange things. So 3 and 4 are space-like from each other, so you can just flip their order because operators at space-like separation commute. And then you're going to have phi 4 here and phi 3 here. And then again, OP between 1 and 3 becomes a sum over a complete set of states. So these operator product expansions will always converge because they're equivalent to sum over intermediate states in this way of writing things. Now, the problem with these expansions is that you can write them down, and they're going to be in principle convergent. But what's going to happen is that as you take this limit, when we boost these operators in our Regge limit, kind of make them go further and further that way, it's going to kind of converge worse and worse. And it's going to be really hard to tell what's going to happen in the limit, because in the limit, infinitely many terms will contribute equally much, basically, to this sum, and there isn't going to be any particular term psi which is going to be dominating this sum. And so it's going to be very hard to try to understand what's going on. It's kind of like, looking at series expansion of e to the power x, which is, sum from n equals 0 to infinity x to the n over n factorial, and trying to figure out the asymptotics as x going to infinity. This sum converges for any positive x, but it really doesn't help you to understand what's going on at large x unless you really look carefully at what this is doing. And here you at least have a formula for every term. In the conformal block expansion, in a general CFT, we don't really know the specific here. And we would require to kind of have a lot of knowledge about them. So the only hope to understand this limit is to do the OP between 1 and 2, and 3 and 4 correspondingly. But this runs into the problem that you're not guaranteed that it's going to converge, because there is no way to make phi 1 and phi 2 be next to each other, and act in a vacuum. And the reason for this is that phi 2 cannot be acting on the fast vacuum because it cannot cross to the right of phi 3. So here phi 2 is to the left of phi 3 because it is in the absolute future of third point, and they don't commute, so you cannot move phi 2 to the right of phi 3. Similarly, you cannot move phi 1 to the left of phi 4. There is no way you can use this over here to argue that the operator product expansion has to converge. So this by itself doesn't necessarily mean that the operator product expansion is not going to converge, but it just means that there is no guarantee that it will. And in this particular instance, it actually doesn't. So in particular instance, it actually doesn't converge. And so now we're going to see why and how to deal with this. Before we do that, any questions? Okay. So let's try to see what is the problem with this expansion. So first, let me briefly review how a conformal block expansion looks like. So we're looking at this 4-point function, 5x1, 5x2, 5x3, 5x4. Sort of the standard statement in conformal field theory is that conformal symmetry fixes the form of this 4-point function up to a function of cross ratios. What this means is that you can write that this is equal to phi x1 to the power 2 delta phi, x34 to the power 2 delta phi. So what this factor does is it takes care of how these operators transform under conformal transformations. When you act as a conformal transformation on an operator, it gets moved somewhere, but also there is some prefactor, like some omega to the power delta. What these factors do is that they take care of these prefactors. Now, whatever else we write here has to be conformally invariant. It doesn't have to have any prefactors. It's just if you move the points around, it shouldn't change. If you move the points around using conformal transformation. And normally, if you look at 3 points or 2 points, it turns out that there is nothing you can write here in addition to the terms which you already have. But for 4 points, there happens to be a lot of freedom in doing this, in that you can write any function g of u and v here, where u and v are the conformally invariant cross ratios. So it's x12 squared, x34 squared divided by x13 squared and x24 squared. For u and v is the same, but you flip 1 and 3. So it's as u, but you flip operators 1 and 3. So this is x32 squared, x14 squared, x13 squared, x24 squared. And often you will also see, instead of, so okay, first, what's the point of this u and v? Is that if you can take some positions of the points x1, x2, x3, x4, you compute what u and v are, then you apply a conformal transformation to your 4 points, you compute u and v again, you find the values are the same as they used to be before the conformal transformation. And so this function here, therefore, is completely conformally invariant, and supplemented with this factor, it gives you things which transform as they should. And you can prove that this is the most general expression. Now, more commonly, perhaps these days, you might find this is written instead of function of uv as a function of zz bar. So x12 to 2 delta phi, x34 to delta phi, and then g of zz bar, where z and z bar are defined by these equations. So z times z bar is equal to u, and 1 minus z times 1 minus z bar is equal to v. Now, if you're working in Euclidean, so the reason why it's called z bar is that if you're working in Euclidean signature, so in Euclidean, signature, if you compute the values, like plug in some actual Euclidean positions for this operator, so there's a distances squared, etc. You compute u and v, then you solve for z and z bar. You will always find that z is equal to, so z bar is the same as complex conjugate of z. So in Euclidean signature, this is true. Z bar is complex conjugate of z. However, in Lorentzian, z and z bar, in principle, are not necessarily related, sort of independent. It's a good question. I'm not sure. I think they might be complex. I think they could still be complex because there are some configurations which are the same. There's still some configurations which are the same in Lorentzian and Euclidean. Like if you just put everything in space like subspace, then so they could be. So usually in Lorentzian, I think they're real but independent. or they're complex conjugate to each other. But I just want to stress that you don't have to treat z as being a complex conjugate of z bar. This is going to become confusing. Like for any concrete configuration, you can compute their values, and you find something. One thing that I should stress, by the way, is obviously these equations here are invariant if you swap z and z bar. So you cannot really tell which one is z and which one is z bar, and accordingly this function satisfies g of z bar is equal to g of z bar z. So usually you just choose some solution and work with it depending on your preference, and it doesn't really matter because the function is invariant under this flip anyway. Okay, so now if we ask about what conformal block expansion means, conformal block expansion is basically an identity for this function g of uv or this function g of zz bar. And what it says is that so what it says is that this function g of zz bar is equal to sum over all O in all primary operators. Then each operator has this OP coefficient phi O Q square. So this describes the coefficient as which O appears in the phi OP, and I'll give a description for it in a second. And this is multiplied by special function called conformal block. So this function, it depends on, so the function is fixed by conformal symmetry, and I'll give you an example. What you need to provide for it is the scaling dimension of O and the spin of O, and also the values of the cross ratios. Now when I say spin, there's something implicit here that it is only the traceless symmetric operators O which appear in the sum, and so when it's traceless symmetric, the spin is just the number of indices, and this is the number that you put here. If you use more general operators, so here we just have a pair of scalars. If you use more general operators, then it's not necessarily true anymore that only traceless symmetric representations will appear, and you can have representations which are not traceless symmetric. And then it will not be enough to specify just one number. In this case, it's enough. Another comment is that because these operators, this is just one and the same operator, this correlation function has some permutation symmetries. For example, if you flip x1 and x2, nothing changes because it's phi of x1 and phi of x2. If you had like phi 1 at x1 and phi 2 at x2, if you flip x1 and x2, then that would be a different 4-point function now. But in our case, we have the symmetry, and what the symmetry implies is that only even j appear in this sum. So j is necessarily an even non-negative integer. Now to explain, so I'll give an explicit expression for this g in some cases in a second. Just to explain what this is, you can describe this OP coefficient if you just write down the 3-point function of phi of x1, x2, and O. Now remember we had this parameterization for local operators O in terms of, instead of writing out indices, we use this polarization vector Z. So if you use this polarization vector, then you're going to get this 3-point function. So we have prefactor, which is just this coefficient which appears in the sum. Then we have a ratio, the numerator takes care of this polarization vector. So we have twice x23 squared times inner product x13 with z minus twice x13 squared inner product of x23 with z, everything to the power j, jo. And then there's denominator, which is just some product of x12, x23, and x13 to some appropriate powers to take care of the scaling dimensions of these operators. So we have x12 to 2 delta phi minus delta O plus Jo, x13 to the power delta O plus Jo, and then x23 to the power, to the same power. So here the point is that, if you haven't seen this before, that the 3-point function is fixed by conformal symmetry to have this functional form, but the conformal symmetry doesn't fix the coefficient in front of it. And so this coefficient is in principle something that describes a theory called the OP coefficient, and it ends up entering into the conformal block expansion. Now, one comment is that if you haven't seen this sort of expressions before, they might look horrible, but rest assured that there are nice ways of obtaining them. So if you first see this, this might look like a mess, but there's an easy way of understanding where it comes from. Another comment is that you also need to, for this to be true, so for this f to be related to this f, you need to specify what the 2-point function of O is. So you need to explain the normalization of O, how we normalize it. And for whatever expressions I'm going to be writing, this is, and also just to give you a flavor of how these 2-point functions look like. This is given by O of x1, z1, O of x2, z2 is equal to, so we just agree to normalize it like so. So we have minus 2 z1 mu, z2 mu, I mu nu of x12 to the power j, x12 to the power 2 delta phi, sorry, 2 delta O. And I mu nu of x is just delta mu nu. So this is in Lorentzian, in Euclidean general, so you have to use the metric e to mu nu minus twice x nu x squared. So again, you can be very explicit with what the 2-point function is, and this is just a convention. You can, again, here we have that conformal symmetry fixes the functional form. We don't know the normalization, but we agree to normalize O so that the normalization is just given by this equation. Now, this is not the most standard normalization you might see. So often you will not have this minus 2 here. This is just depends on the convention. If you're never working with these things, you have to be careful about what conventions you're using. Similarly, here in this expression, you might not see this factor of 2. This particular convention turns out to be nice for this sort of applications. So if you use this, these conventions, you can give sometimes an explicit formula for the conformal block. And this formula, so the conformal blocks, they are not generally known in closed form. However, in even number of dimensions, in even number of space-time dimensions, you can generally write closed form expression for them. So for example, in d equals 4, so the same as 3 plus 1, the formula for this conformal block g delta j, or z bar, is as follows. It is z bar divided by z minus z bar. Then we have k delta plus j of z, k delta minus j minus 2 of z bar minus z and z bar exchanged. So the same factor, but z and z bar swapped. And k beta of x is a special function equal to x to beta over 2 times hypergeometric function to f1 of beta over 2, beta over 2, beta x. So we're going to, so this is the example of a particular conformal block which appears in the 4-point function of scalar operators in 4 dimensions. If you go to more complicated operators, say in 4 dimensions, you'll still be able to write formulas like this. They're going to be much more complicated, but you can do this. If you go to something like 3 dimensions, then we don't know any closed form formulas, but there you can use other tricks to compute these functions or figure out their properties without explicit expressions.
And do and know equals to expression in terms of UV values in the equal to.
Yeah, you can just solve for z and z bar in terms of u and v and plug it in here, and that's the answer. It's going to be a bit annoying, the expression. U and v variables are not the best variables for this. So my point is just that today we are going to be using this explicit formula, just pretending that we only work in d equals 4, but whatever I say is going to be valid more generally. I just don't want to spend proving that all the blocks satisfy some properties, although you can do that by spending more time. So these are very well studied special functions. Just in principle, there is an explicit expression. So one thing that we will need about this special function k beta of x is its large beta behavior. So at large beta,
what's the best that one can do in 3 dimensions? Like, can you express it block as some of jack elements or something, but it just won't be enclosed form?
well, there are some, if I remember correctly, there are some explicit expressions, which I don't remember. Explicit expressions, but not like closed form expressions. You can write this as some crazy nested sums. There are special cases if you take identical scalars and set z equals z bar, then I think this can be written as like 3 of 2 or something like this. There are many different expressions you can write which are reasonably explicit. Just different expressions make different properties of the conformal block more explicit. In some sense, it's like, do you know 2f1 explicitly, or do you know Jacobi functions, like Jacobi polynomials explicitly? Well, you do in the sense that like you can go online and like in digital library of mathematical functions or whatever, find lots of properties of them in various expressions, or like compute them in Mathematica. So conformal blocks are sort of the same status, just less well known. Like you can write many expressions for them, you can compute them numerically, we have very efficient algorithms for this. Just that you cannot maybe reduce them to like. So I wanted to give this result that k beta at large beta so when beta can be in principle any complex number, just large enough. K beta gives us 1 over square root of 1 minus rho squared. So let me write it k beta of z, square root of 1 minus rho squared. Then there's 4 rho to the power of beta. And then you get 1 plus 1 over beta corrections. So the leading asymptotic is this, and then there are kind of multiplicative 1 plus something corrections. And rho here is given in terms of z, 1 plus square root of 1 minus z squared And if you want to go back, z is given by for rho, sorry, just for rho divided by z is given by 4 rho divided by 1 plus rho squared. So the reason why this row looks very much like this row is because they're the same, so you can check that for this configuration that we discussed in Regge limit, if you compute u and v, solve for z and z bar, plug z into the expression for rho, you will find that this row is the same as that row. The fact that you cannot distinguish between z and z bar, so if you make the right choice, you'll find that rho here is equal to rho there. Correspondingly, if you want rho bar, you'll put bar here and bar over z. Okay. So one thing to note while we're talking about this relation is that eventually we want to make rho bar to be large, positive and large, and when we go from rho bar being like small to rho bar being large, we want to use this epsilon prescription by giving it small negative imaginary part. So if you look at this formula, then when rho is real, z is real, if rho goes to 0, then z goes to 0. This is just, you get 4 rho, which is small, and the denominator is approximately 1. But if rho is large, then this also goes to 0. Z goes to 0 because, maybe let me write rho bar. So if rho bar is large, then z bar goes to 0 because you have rho bar squared in the denominator, but only rho in the numerator. And so in our limit, when rho bar becomes large, the bar is going to go to 0. However, it's going to go to 0 only after crossing some branch cuts. And these branch cuts have to do with the region of convergence of this, kind of a priori region of convergence of this expansion, which is that in the plane of ZZ bar, well, in the complex plane of Z, and the same is happening in Z bar. So this is imaginary part, this is real part. There is a cut starting at 0. There is a cut starting at 1. And so this is the picture both in Z and Z bar. And this conformal blocks, they have, that's their analytic structure. And the expansion converges everywhere in complex plane of Z and Z bar except for this cut. So in this cut, the expansion stops converging. At another place, it does converge. And where it converges, the function of ZZ is analytic. Now, when we start with rho reasonably small, rho bar reasonably small, remember we start from small rho bar and then we make rho bar bigger. Our Z bar sits maybe somewhere here. It's between 0 and 1. And then we make rho bar bigger. When rho bar is equal to 1, you get 4 divided by 2 squared, so it's 1. So when rho bar is equal to 1, Z bar also approaches 1. So the point when rho bar hits 1, which is when the, say, 0.2 hits the null cone of 0.3, Z bar hits this cut. And then when rho bar keeps increasing, this starts decreasing and Z bar goes back. So to figure out what's going on, because it sort of approaches this point and then goes back, to figure out what it's doing exactly, we need to remember about this epsilon prescription and see what exactly happens when rho is close to 1 to the null cone. When rho bar is close to 1, you can show that this is 1 plus, or 1 minus, sorry, I forget the sign. Yeah. Well, Let me just say it in words because this is getting too technical. So if you, instead of moving along the real axis, you actually shift it a little bit here to the negative imaginary part, you'll find that z, instead of just going to 1 and going back, z bar, what it does is it goes around 1 through the cut counterclockwise. And then it goes to 0. So the prescription that we're going to have for our conformal block expansion to try to go to the Regge limit is to start with the conformal block expansion in the region where it converges, then take z bar around 0 counterclockwise, and then send it to 0. Specifically, we are going to be looking at the situation where rho is equal to r times omega, where bar is equal to r times omega inverse, and omega goes to 0. So in this case, rho bar becomes very large, and rho becomes very small. So because rho is getting small, it means z is getting small, and because rho bar is getting large, it means z bar is getting small, but not before going around this branch cut. And because z bar crosses this branch cut, this is where we're going to start having problems. So in the end, the limit is both z and z bar go to 0, but with this twist that z bar goes around the branch cut. And if you, so I erased this, but if you look at the definitions of, u, v, z bar in terms of x1, x2, etc., then the usual kind of the simplest limit when x1 just approaches x2, the operator product expansion limit, it's described by z and z bar going to 0. So this limit kinematically in terms of z and z bar is very similar to the usual OP limit, but with this extra complication that z bar does funny things. Any questions? All right. So let's try to figure out what's going on with this expansion first in Euclidean signature when we don't have any troubles, and then in this Regge limit. So when we're summing over operators, both the scaling dimension and the spin of the operator can get very large. Because scaling dimension is kind of like the energy on the cylinder, and this can be arbitrarily large, so there exist operators with arbitrarily large scaling dimensions, and similarly there exist operators with arbitrarily large spin. And so the sum is kind of a doubly infinite sum, if you wish, and both of these parameters of form block can get large. Now, if you look at this expression, when delta is large or j is large, or both of them are large at the same time, provided that they don't scale exactly in the same way for this to remain constant. So when these parameters are large, then generically for both of these k functions in this expression, we can use this asymptotic formula. What do we find then? So we find that g delta j and I'm going to just look at this sort of exponential terms. So there is 4 to the power beta, and we have 4 to the power delta plus j, 4 to the power delta minus j. So, sorry, this is beta over 2. So altogether, this will give you 4 to the power delta. So this is the first exponential factor. But then there is, of course, going to be some exponential behavior from the cross ratio. So we're going to have rho to the power delta plus j times rho bar to the power delta minus j over 2. So again, I'm just keeping the things which scale exponentially. And if you use this parameterization of our limit, then this is just, this term becomes 4 to the power delta, r to the power delta, omega to the power of j. And the second term is the same, but with z and z bar flipped, and flipping z and z bar is the same as flipping rho and rho bar, which is the same as flipping the omega and omega inverse. So this second term is going to behave like 4 to the power delta, r to the power delta, omega to the minus j. So in Euclidean signature, what I said was that z and z bar are complex conjugate to each other, which means that rho and rho bar are also conjugate to each other. And when they're parameterized in this way, this implies that r is real and omega is just a phase. So in Euclidean signature, r is a positive number, and if you're careful, you can actually check that it's between 0 and 1 generically, and omega is just some phase e to the I theta. And then looking at this large delta or large j behavior, we see that there is no problem with large j because omega is just the phase, so nothing's happening. That doesn't grow or anything. And then r to the power delta just gets smaller and smaller as delta gets larger and larger, because r is between 0 and 1. And so in Euclidean signature, this expansion converges nicely, and all is good. However, when we go to our Regge limit, we know that we have to take this parameterization when omega is actually not a phase, but instead it's a small number. And then we should get immediately suspicious about this term, because for for positive j and small omega, this term is very big and gets worse and worse as j goes to infinity. But in fact, even if we didn't have this term, even if it was just this term in Euclidean signature, then it would be still in trouble. And the reason for this is that this expression that asymptotic behavior that we wrote here is for this formula. This formula is valid in this cut plane, and when you start crossing the cuts, the formula changes because these functions are not single valued as you cross the cuts. And the bar crosses the cut. Now the bar crosses the cut, and something happens, for example, to this function k, because this hypergeometric function has a cut at x equals to 1, and when you go around this cut, it has some sort of monodromy. What you can check is that if you take k beta of z bar, and you send z bar kind of counterclockwise like so, it's going to become a linear combination. It's not important with which coefficients of itself, and the same function, but with 2 minus beta instead of beta. So when you keep, this is just follows, from some properties of hypergeometric function. There are well-known formulas for how you can find it kind of in reference material, some kind of references for special functions. What happens to a hypergeometric function when you take its argument around 1? It becomes the sum of two hypergeometric functions. In this case, it ends up implying this for k beta. K beta becomes the sum of k beta and k2 minus beta. One way of seeing why this is the case is that actually it turns out that k beta and k2 minus beta are two independent solutions for a particular second-order differential equation. And when you take monodromies of solutions of differential equations, they become linear combinations of other solutions. So that's generically what you expect. So when this happens here, there are a few terms kind of a few new terms that appear. So in addition to these terms, that we have here, we're now going to have terms which look like, so say we had k delta plus j z, we have k delta minus j minus 2 z bar. Now this guy will produce itself after the monodromy plus something related. So in addition to this, we'll now get k delta plus j of z, and then k4 minus delta plus j of z bar. And similarly, there is another term here which looks like k delta minus j minus 2 of z, k delta plus j of z bar. And after monodromy, it's also going to produce a term related to this one. So k of delta minus j minus 2 of z, k of 2 minus delta minus j of z bar. And so now when we analyze large delta, large j behavior, we have in principle to include all of these terms. They'll have some coefficients, which we are not computing. But after the monodromy, the conformal block gets all these terms here. And it's not just this sort of guys that we're going to get. Any questions about what's going on so far? All right. So just to clarify what the logic is, we're looking to start from this expansion, which works beautifully in Euclidean signature, and we're just trying to blindly apply it to the Regge limit. To apply it to the Regge limit, so there is some messing around with some cross ratios, etc. But in the end, this is the prescription. You take the Euclidean conformal block expansion, you take z bar around, and you send z in z bar to 0. That's what we are doing. And this limit, we can parameterize it in terms of rho and rho bar in this way by r and omega going to 0. So that's all that's happening. We are just trying to see what's going on with the conformal block expansion, with the box standard conformal block expansion in this limit. And after we take the monodromy, we find that the conformal block gets more complicated because it's not a single valued function. And these are the terms which appear in this conformal block after the monodromy. Now we know how one conformal block behaves. Well, we know that if you have a term of this form, so let's just write it more explicitly. So if you have a term inside of our conformal block of the form k alpha of z, k beta of z bar, by using the asymptotic formula for k when alpha and beta are large, this contains a term which is going to be rho to the power alpha over 2, rho bar to the power beta over 2. And using this is going to be rho to the, r to the power alpha plus beta over 2, and then omega to the power alpha minus beta over 2. So now I'm just going to replace each one of these terms by this sort of expression to see what's going on. So this term is going to be r to the power delta, omega to the power j. This term is going to be r to the power j, because when you add this up, delta cancels, but then omega to the power delta. Now this term is going to be, again, r to the power delta, but omega to the power minus j. And this term is going to be r to the power minus j and omega to the power minus delta. Sorry, still delta? It doesn't sound right. Okay, omega to the power delta r to the power. Okay, let me just finish this thought and we're going to take a break. In any case, you see that we have this term, which is going to give us trouble when omega is small and when omega is small and j is getting large. I get a bit confused. I think I must have made a mistake. There should also be a term omega to the power minus delta, which also will give us trouble. Delta can be large. So we are going to have problems because delta being large and because of delta being large and j being large due to this fact that omega is not a phase anymore after the monodromy. And so our goal is then to somehow cure this, and to cure this we'll have to come up with some tricks which come by the name of Sommerfeld-Watson resummation, which will lead us to Lorentzian spin. But let's take a break and then continue after the break. So where did we stop? So we stopped on the conclusion that we are getting problems from large delta or large j in the Regge limit. And we're going to cure these problems one by one. First, we're going to deal with large delta because this doesn't require any kind of new dramatic ideas as compared to curing large j. So what we do at large delta is use so-called conformal partial wave expansion, which is just a cousin of the conformal block expansion, which is kind of a bit less common. You might not have seen this even if you know conformal block expansion. So conformal partial wave expansion comes from conformal partial wave expansion is in a way a kind of Euclidean cousin of the conformal block expansion. And to see how this works, let me just say a few words about this sort of standard expansion. So I mentioned that when conformal block expansion, well, one station in which you can guarantee convergence of the usual conformal block expansion is when you have an ordering of operators of this sort. So say phi1 and phi2 act here on the vacuum, and then the conformal block expansion is related to the idea of inserting a complete set of states here is an intermediate. So we're just summing over some basis of states in the Hilbert space, and we're looking at these terms. So this, in principle, we could take many different bases of the Hilbert space, and this would always work. But this expansion is associated to kind of a special choice, which is.
So wasn't there a problem that one you cannot take to the extreme out with the configuration you discussed?
Yes. So this is not the 4-point function we're looking at. But if we were looking at this, then this expansion would be related to this trick of just inserting a complete set of states in the middle. So this is not the Regge limit. This is not Regge. We'll come back to Regge in a second. So the way to get conformal block expansion is to arrange the states psi according to the representations of the conformal group. I'm not going to go do this explicitly. I just want to stress that these are states in the Hilbert space, and we discussed that this conformal group SOD, 2, the universal cover of SOD, 2 is the thing which actually is represented in the Hilbert space. So if we take this representation of this group, we decompose the Hilbert space into reducible representations, and then arrange this sum kind of reducible representation by reducible representation, then this will give you this conformal block expansion where each term corresponds to one reducible representation of this guy in your Hilbert space. A very physical idea. You have your Hilbert space of states, decomposing it according to a symmetry. Each term, and if each multiplet gives you a contribution in this sum. And the conformal block just comes from summing up different states in the same multiplet. So this is the usual conformal block expansion. The conformal partial wave expansion is a similar idea, but it uses representation theory not of SOD, 2, but of SOD plus 1, 1. So conformal partial wave expansion, usually called CPV, CPW. This is in some way replacing SOD, 2 by SOD plus 1, 1. I'm not going to derive it in this way. I'm going to present a much more kind of elementary point of view. But general idea is that again, here the conformal block expansion you can get by arranging everything in representations like psi's in representations of SOD, 2. And the way you can detect it, which representation this is, you can act on psi. But alternatively, because this 3-point function is invariant, instead of acting on psi, you can move your transformation to act on phi 1 and phi 2. And so you can view this expansion, or conformal block expansion, as arising from this picture when you just start acting with SOD, 2 on phi 1 and phi 2, and asking how this transforms, basically decomposing this into different irreducible components with respect to the transformation law. And this point of view, when you don't think about this as kind of breaking down it up in separate states psi, but just taking this expression and asking what sort of decomposition you can get by studying the action of the group on points phi 1 and phi 2. This translates also to the Euclidean. You can now take the action of SOD plus 1, 1 on Euclidean points in the 4-point function, just on the pair of them, and decompose that action with respect to kind of reducible representations. And this way you'll get this conformal partial wave expansion. This is the conceptual point of view. I'm going to kind of state a much more down-to-earth approach. Though I want to stress that even though there is this analogy, this group doesn't act on any nice Hilbert space. This does. This acts on our Hilbert space. This one doesn't. So this conformal partial wave expansion is not directly related to any representation theory in any Hilbert space. It's just a trick to get a different form for the conformal block expansion. So the way this conformal partial wave expansion looks like is very similar to this, except that instead of a sum, we now have a sum and an integral. So it gives for g of zz bar, gives this sort of form. We have a sum over spins, j, and we're summing over even integers, because only even integers appeared in our formula. And we are integrating over delta null. We are integrating from d over to minus I infinity to d over 2 plus I infinity. So this is an integral in complex plane. So in the complex plane of delta, normally here we will have a sum over local operators, which will have some real scaling dimensions. So they're going to be sitting somewhere in this axis. And we're just going to be summing over these terms over there. Here, instead of doing this, in conformal partial wave expansion, we're integrating over a line at d over 2. And the integrand, so what we're integrating is some function c delta j, c of delta and j, times f delta j of zz bar. So this is the conformal partial wave, what sometimes is called conformal partial wave. I should warn you that the literature isn't very consistent on the names. I tend to call these guys conformal blocks and these things conformal partial wave. So conformal block expansion, conformal partial wave expansion. In the literature, you sometimes will see people call this conformal partial wave expansion. That in conformal blocks it will also get called conformal partial waves, and then I'm not sure what the name for this would be, but you should be aware that this is not very consistent. So these functions, they're analogous to conformal blocks and can be expressed, in fact, in terms of conformal blocks by saying that f delta j of zz bar is 1/2 of g delta j of zz bar plus some coefficient. So this coefficient is some gamma functions of delta and j times g of d minus delta j zz bar. So here it's the same conformal block. The only thing that changes is the coefficient front, get some factors of gamma functions, and delta is replaced by d minus delta. Yeah, that's so replacing delta by d minus delta is called the shadow representation. So you have representation which is specified by delta and j, then the representation specified by d minus delta and j is called the shadow representation. Sometimes this is called the shadow conformal block, and we say that conformal partial wave is a combination of the usual conformal block and the shadow conformal block.
And this relation is true for complex vector, or only here?
For any delta. That's just a formula between some special functions.
And when you drew this complex plane, like if you have a scalar over here, like d minus 2 over 2 scaling dimension that leaves on the other side of the line.
I haven't said what happened, what I do precisely here, probably, but let me explain first the relation between this and conformal block expansion, and we'll see what happens if you have scalar operators, as you said. So normally here you'll have to also write equals to 1 plus the sum, so you'll separate the contribution of the vacuum of the identity operator. So one of the operators that contributes here is just O equals identity, the simplest operator, in which case the SOP coefficient is 1, and the conformal block is equal to 1. So it contributes just 1 to the whole sum. And often see it separated. Sometimes you'll see people just ignore this and not write it.
So the 4-point function or function is not connected, like from the function whatever you will get the 4-point function, which should be, there should not be really identity over there.
No, path integrals, no. So there are things called connected correlation functions, and you get them by taking variational derivatives of the kind of free energy of log z. But I'm not talking, sorry, I'm not talking about those. I'm talking about just variational derivatives of the partition function. So you could call them disconnected or whatever, the full complete correlation functions. So I'm including everything. if you talk about connected correlators, you'll have to be more careful with the conformal block expansion. Subtracting identity is one thing, but then you're also subtracting identity in cross channels, and that modifies it by a bunch of double twists. So what's the relation between this formula and that formula? The claim is that this function C delta J, it replaces these coefficients F, phi, O, and in what, kind of to some level, you can treat this as to some degree, you can just treat this function as simply being designed to have this property that for a given spin, the function has simple poles at every scaling dimension of, like its scaling dimensions of all the local operators. So it has poles where you used to have local operators with a peak with residues proportional to, well, equal to minus OP coefficient squared. And the relation between this integral and the sum over conformal blocks is that if you have this integral, then you can take this expression for the conformal partial wave, plug it in here, focus just on this term first. And this term then looks like just an integral of C delta J times the conformal block instead of the conformal partial wave. And C delta J has poles which have the residues equal to these coefficients over here. And so what you do is just deform this contour, you pick up these poles, and you recover 1/2 of your sum. You get 1/2 because there was this coefficient 1/2 in front of here. What happens to the other half? If you focus on this term, then for this term you have to use the property that this function has, which is that C d minus delta J is equal to some prefactor again, which is some gamma functions, which depend on your conventions, times C delta J. So it has some so-called shadow symmetry. It's shadow symmetric. And together is the fact that you have a shadow scaling dimension here, when you focus on this term, you can replace here the C delta J with C d minus delta J, and the coefficients are going to cancel. And then that integral will deform into the other half plane, and you pick up the contributions again of the same poles, and you get, again, 1/2 of your sum. And together, they give you the full sum. So again, just to recap, focus on this guy, times C delta J. You do the contour deformation using this property, get 1/2 of the sum. Then you focus on this guy. You do the same thing, but now you also use this property that C is shadow symmetric, and you get the other half of your sum. And altogether, you recover the conformal block expansion. So to some extent, you can just think about this function C delta J as being designed, as having been designed to have these properties so that you can play these tricks. Then you can ask, well, why I care about this special combination of F delta J, like this special combination of block and the shadow block? And the answer is that this combination has nicer properties in Euclidean signature. It doesn't have some cuts. So sometimes they say it's single valid in Euclidean signature. So it exhibits the property that like the correlation functions in the Euclidean signature are nice and smooth everywhere. This property isn't going to be important for us, but this is one way to think of thinking why this is important. Of why is this an important combination?
And this also helps to throw the arc contribution.
Well, in the end, yeah, you can throw the arc contributions if you do the careful analysis. That said, so you can view this function as just being designed to have these properties, but there's also just a formula for it. in terms of some integral of the 4-point function. So you can compute this function c delta j by multiplying your 4-point function by a conformal block or by a conformal partial wave and doing some integrals. And so there is a constructive formula for which you can check that these properties are true. And what you can prove based on this formula and on these relations is that this function c delta j has a bunch of poles. It's a meromorphic function. It has these poles related to local operators. So they encode the scaling dimensions of local operators. But it also has some kind of kinematical poles which are necessary due to conformal symmetry, which have to do with the fact that the story of deforming this orange contour to pick up these poles is a bit more complicated than I made it sound. And the main reason for this is that this function g delta j itself has poles in delta. So g delta j is not defined for all values of delta. For some values of delta, it has poles. And besides these poles from local operators, you're going to pick up the poles from g. And to actually not have these poles contribute to the final result, you need c delta j to have extra additional poles, which will cancel these poles. So there is some technical stuff going on where you have so-called spurious, if you wish, poles for c delta j, which are not related to local operators. But this is kind of dictated by kinematics. If you think about conformal symmetry very carefully and think about all the properties of these functions, then this all fits together and these poles don't matter. They're there in some sense for a technical reason. So we pretend basically that this is the only thing that happens to this function. Now, to answer the question of what happens if you have a scalar operator below delta over 2, then yeah, you basically need to have a scalar operator here. You need to do this. Any questions about this claim? I haven't yet explained why this is an important thing for us to do, but just at technical level, any questions of how this works? So in a way, the idea is that we turn the sum into an integral by the residue theorem, and in a way, we can think about this as just starting with the sum and trying to do a trick where we just insist on turning the sum into an integral, but in fact, there is some reason for why this integral exists in the first place from kind of Euclidean perspective. The reason why this integral is important for us is that in it we are integrating over delta, but only in an imaginary direction. When delta becomes large, it is the imaginary part of delta that becomes large now, not the real part of delta. So if you have some number raised to the power delta, you don't have to worry about that anymore. So for example, if we had omega to the power minus delta, so this would have been problematic before when omega is small and delta is large. But now, no matter what omega is, as long as it's a real number, because we're integrating over imaginary delta, there is nothing special happens to this because it's just a phase now for imaginary values of delta. So this cures whatever problems we might have had from summing over delta. This doesn't do anything to our problems from summing over j, because we are still going to have in our conformal blocks after the monogery terms which have omega to the minus j inside of them. So this is still there. J still, we're still summing over j in this expansion. So j can still get large. Omega is less than 1. This leads to divergences. So next step is to solve the problem of large j. And solve the problem of large j, we do the same trick. We replace the sum over j by an integral over j along imaginary direction. So we're going to replace the sum by an integral. To do that, historically, the way it worked is that people first figured out that you can do that, and then they figured out why you can do that. So here, when we did this for delta, we relied on the existence of this function c delta j. And I just said that you could have tried to design this function in this way, but also you can prove that it just exists by writing a formula for it, so-called Euclidean inversion formula. When we do the trick for j, originally people just assumed that you can come up with a similar function, which we'll discuss now. But now we also know that there is a Lorentzian inversion formula which also gives you this function. So to go from a sum over delta to an integral over delta, we use basically Euclidean inversion formula, and to go from the sum over j to an integral over j, we use what's called the Lorentzian inversion formula. So let's see how this trick with replacing sum over j by an integral over j works. So let me first rewrite this in a bit more readable manner. So I'm just going to replace our conformal block expansion from partial wave expansion, which is slightly nicer now. So we have, say, 1 plus sum over j given integers. I have integral over delta over that contour. Then we have c delta j, and then our f delta j of z bar, where f is the conformal partial wave, which is the sum of conformal block and shadow block. We're going to do first the simple thing that after monodromy in z bar, this conformal partial wave, it's going to get a it's going to get various terms which are problematic, which will have like omega minus j. Then it's going to have terms which are not problematic, which have omega to the power plus j in them. So these guys we're just not going to care about because they're not problematic, and they all go to 0 as omega goes to 0. The important things for us are going to be these terms. And so everything that contains this sort of omega to the minus j, I'm going to denote it by sort of curly f delta j of z bar. So now our goal is to try to cure this integral for these terms, cure the sum over j for this sort of terms. And I'm not going to be super careful about it because in principle, whenever you do these tricks with contour deformations, you have sums, some contour integrals, you do deformations, infinite sums, you have arcs at infinities. Bisogit was pointing out, you have to, in principle, do analysis to make sure that everything is bounded as you want it to be bounded at various directions. I'll say where these bounds can come from, but I'm not going to be doing this very systematically just because it will take forever to check all the properties. And also you have to be kind of careful with your steps. You have to specify that, oh, first I start in the region where the sum converges and I turn the integral and the integral still converges, and then I do an analytic continuation of the integral around the branch cut so that the integral is perfectly fine during this entire path here when I go through the branch cut. So I have to be careful with this, which I'm not going to be to just go faster. If you want the details, I'm happy to give you references. So let's do this. I'm going to replace this by the problematic term. And we're just going to be focusing on this term.
Did the original paper do all these analysis checks?
They were eventually all done in various places. Yeah. So probably the best reference, if you want like everything super carefully, there's this paper. It's called Regge Theory at Finite Boost. One of the authors is Simon Cohen-Ho. You can find it for you if you want, where they just do everything very carefully. They keep all the terms, don't throw anything out. So because what I'm trying to do here is just determine the leading behavior as omega goes to 0. But you can also ask what's the full answer as omega is just small. Like say omega is 1 over 100 and I don't want to know the leading behavior, I just want to know the full answer. Then that's involves being more careful in keeping all the subleading terms and figuring out how to do things properly. And so that paper does the thing at finite boost. So that's as probably good as you're going to get. So here we are summing over these terms. And what we're going to do is to formally first basically do nothing to this sum in the way of adding a denominator like so. We're going to add 1, like c delta j over 1 minus e to the minus I pi j. And what this does is that it creates a pole at every even integer. And then we are going to replace the sum correspondingly by integral over j over some contour gamma. But this contour gamma is very boring. So analogously to what we had here for delta, in the complex j plane, we are going to, so we started off with a sum which went over, for example, 0, 2, 4, and so on. We're going to, how we define this contour gamma is that it just goes around each of these poles. Counterclockwise. Sorry, actually, let's make it go clockwise. Doesn't matter. Up to a sign, that's fine. So we had the sum. Now I introduced by hand these poles, and I changed the sum into the integral. But this is a trivial transformation just because with the contour I picked, I can immediately close every one of the small circles and just get the same sum back. I didn't really do anything dramatic in this case. Except that, of course, I'm pretending here that this function c delta j can be analytically continued in j, so that I can even make sense of what I'm doing here. So for now, I'm just going to pretend that this function c delta j has an analytic continuation which satisfies all the properties I could possibly want from it. And then I'll comment on why this actually is true. So we have this analytic continuation. Well, we have this integral now. And the idea now is simply to take all these circles and turn the contour, the integration contour, into a contour of this sort. So we're deforming all these circles, kind of blowing them up and deforming it out to this contour over the blue line and dropping the arcs at infinity. So to drop the arcs at infinity, you have to assume some behavior of the function. And also you have to assume, of course, that the integrand is going to be holomorphic in this right half plane. So it turns out that it is almost true except for the holomorphic part. And in general, when we do the deformation, we're going to find that there are some additional poles which can show up somewhere in the complex plane. And if they do show up, then we have to pick them up when we do the contour deformation. And let's say, for simplicity, let's imagine that we found one such pole, and this pole was at some little j of delta. Because for different values of delta, this pole can be at different positions, potentially. And so if we do that, then this becomes the integral. So there is 1, minus 1/2. Integral, let's call this blue contour now gamma prime. Integral over gamma prime. into j delta over to I c equal to j, or 1 minus, sorry, j. And so what we achieved by this is that after the deformation is done, well, let me call this contour gamma, let me call just this part, and this term, let me write it out separately. So I'm just going to write it out as minus pi I integral d delta, and then residue at j equals little j of delta c delta j 1 minus j times this f delta little j of delta z bar. So if I forget about this term, which came from this extra pole, and I just look at the integral is over this contour gamma prime, and gamma prime just runs over imaginary direction. So whenever j becomes large now, it becomes large in the imaginary direction, and so the sort of factors inside of here, which were omega to the power minus j, don't bother me anymore because omega is small, but that's fine because the only way in which j can be large is by having large imaginary part, and so this is not contributing poorly to the integral. And so this integral now converges, and I can use it to analyze what's going on. But also, of course, because I still have this terms, I can analyze, and so since now they're kind of perfectly fine, I can analyze here uses omega going to 0, and kind of how this term grows or decays is determined by the real part of j. So the absolute value of behaves as omega to the minus real part of j. So if I focus on the absolute value. So in the integral, the real part is bounded, and we can just agree to push it as far left as we want and pick up various poles, such as this little j of delta. And so in principle, by pushing this gamma prime further and further to the left, we can make this integral as small as we would like, at the expense of maybe adding more terms like this, which pick up this extra poles. Now, if you look at this term, then this term behaves as omega to the minus little j of delta. In fact, if you're careful and keep all the factors, you'll find that this is omega to the 1 minus little j of delta. And so in principle, because I assumed that we did pick up this term after deforming the contour, this real part of little j is greater than the real part of our contour, so it gives the more dominant contribution. And the larger is the real part, the more dominant this contribution is going to be. And one of our assumptions is that there is just going to be some pole is the largest real part. You don't get a sequence of poles which span all the way to the right. And so the bottom line of all this is that once we did this contour deformation, now we have a good representation of the 4-point function Regge limit. And with this representation, the leading term at small omega is given by this expression. To find how your 4-point function behaves in the Regge limit, you have to construct this analytic continuation C delta J, which satisfies nice decay properties so that you are able to do all these tricks. And then look at what is its rightmost pole in J when delta sits on its contour, which is drawn here. So we need to ask when delta is on this contour, let's assume that we don't bother with this little one here. When delta sits on this contour, what's the largest value of real part of little j of delta that appears, and that will determine the behavior of the 4-point function in Regge limit. So again, omega goes to 0, so this is what dominates. So this doesn't explain why this C delta of j exists, but the statement is that similarly to the trick we did with delta, there exists a formula for this C delta j, and this formula is known as the Lorentzian inversion formula. So what you can prove is that C delta j can be computed, and I'll say more words about this next time, but the C delta j can be computed as an integral over ZZ bar, some prefactors, times so-called double discontinuity of your 4-point function g of ZZ bar, times a conformal block with some particular indices. To derive this formula, you start with the Euclidean inversion formula, and you do some clever contour deformations in the Euclidean inversion formula to get this result. Once you get this result, this distinguishing feature of this integral that you can check is that it's analytic in this little j. So it defines the analytic continuation of j to the complex plane. And you can prove that it's analytic in j, provided that your function j of ZZ bar doesn't grow too quickly in the Regge limit. So if you know that your function doesn't grow too quickly in Regge limit, then you can show that this integral converges, and this defines C of delta j. And it shows that it's analytic in right half plane, and the better g of ZZ bar is behaved in the Regge limit, the further to the left the function is analytic. And this is precisely due to the statement that as soon as the C delta j develops singularity, so as soon as it stops being analytic, this determines how bad your function is in the Regge limit. So of course your function could have been terribly bad in Regge limit, just grow faster than any power, which should sort of correspond to singularities spanning all the way to infinity on the right. But as we'll see next time, there is a very short argument which says that this isn't true. And in fact, g of ZZ bar has to be order less or equal than something of order 1 in the Regge limit. So this will show that in Regge limit, the 4-point function just cannot grow, it's bounded. And this implies that Lorentzian inversion formula provides for C delta j which satisfies all the properties, and then you can run this argument. And because you know this, and because you know that this is the dominant contribution, this also shows that this real part of little j of delta has to be less than 1. Otherwise, if it was if it was greater than 1, then this term would blow up in Regge limit, which is not possible. So this last part I went very quick just to get to the point. In the beginning of next lecture I'll say this in a little bit more detail, why this is true and how the Lorentzian inversion formula comes about. And then the last lecture we'll also discuss how this is connected to Lichy operators and what else can you do with these analytic continuations. Any questions? Yeah.
Is that last thing that you wrote related to why they say that like this C delta j is only analytic spin for j is greater than 1?
Yes, it's related. So when people say that, so physicists are never careful what they mean when they say analytic, and this phrase C delta J is only analytic in spin when J is greater than 1 can mean many different things. Not many, but at least 2, which is a lot. Uh, so when J is greater than 1, like in here, you can just prove that this is analytic. As in, it cannot have any poles. It just like is an analytic function in mathematical sense. Now, sometimes people will say analytic when the function actually has a pole, but you can still go past this pole. So it's like analytic to the left of the pole as well. And so this could still happen. You can only prove that it's like the only thing that we can prove is that it's literally analytic without any poles or anything to the right of J equals 1. Then to the left of J equals 1, it could have like a pole, but then it can continue to be analytic. So this can happen. So it could be analytic in that sense, more than just for J greater than 1. But what could also happen is that it's like not analytic in a worse way than just having like some poles. So when I say that it's analytic, I imply in particular that if you set J to be an even integer, you reproduce like the non-analytically continued function, the function that you get from Lorentzian inversion formula, the function that you would use in the conformal partial wave expansion from which you can extract the local operator data. So analyticity of spin, part of the idea of analyticity in spin is that you can start with maybe large spin, analytically continue down to spin 2, and you'll just get the local operator data at spin 2. What can happen is that if you try to go to spin 0, then the analytic continuation that you get from Lorentzian inversion formula will actually not agree with the local operator data at spin 0. And that particularly happens in some perturbative calculations that people do in 1/n sometimes. Though I tend to think about this as more of an artifact of the perturbative expansion, and I don't have any evidence against the claim that modulo like this isolated poles, the C delta J might just be analytic down to spin 0 in all cases, if you think non-perturbatively. But that's not something you can prove. Sorry, that probably was too long of an answer. Any other questions? Right, thank you. Let's finish here then.